Hey guys, welcome to 2.1, the derivative and differentiability. Now, in the last video, we defined what a derivative was. So to put it in simple terms, a, a derivative simply means slope, but not just any slope. It's the slope of the tangent line. So recall that you discussed two types of lines in geometry. You discussed a secant line, which is a line that crosses the curve at 2 points. And you also discussed a tangent line, which touches the curve at 1 point. Now, in the last video, I had said that the secant line represented an average rate of change, an average, but the tangent line represented an instantaneous rate of change, which we call the derivative. So the derivative is a slope of the tangent line, or the instantaneous rate of change, IROC. Now, looking at the definition, so the very first sentence says, a function f is said to be differentiable at x equals c. In other words, at a certain x value, if the derivative of f exists at x equals c. So if you were to take the derivative of the function and plug in a value for c in x and you get back a number, then the function's differentiable. That's pretty much what it says. Now, the next part says, in order for the derivative to exist at x equals c, the graph must have local linearity. Okay, so pretty much what this means is that if you were to zoom in on a certain point of the graph and you were to continuously zoom in, the curve of the graph will start to flatten out like a line. In other words, if it does flatten out like a line, then the derivative must exist. But I'm going to give you guys an easier way of defining what differentiable function looks like. A differentiable function. A differentiable function is smooth, smooth and continuous. Okay, so we talked about continuity in the last unit. Continuous function is a function that you can draw without ever lifting up your pen or your pencil. A smooth graph is a graph that looks smooth. In other words, no sharp points, no jagged edges, none of that stuff. Okay, so a differentiable function is a smooth and continuous curve. So let's go ahead and, to better understand what differentiable function looks like, let's go ahead and look at some non-examples of non-differentiable functions. So in example number 1, a function is not differentiable at x equals c if, so here's one of them. One says if it has a sharp turn at x equals c. So look at this graph. This graph is the absolute value function. We know that the derivative exists from the left of 2 because it's a line going straight down. There's a slope, so the derivative must exist. We know that there's a slope after 2 that's going up. Since the slope exists, the derivative must exist. But we can't define the slope at x equals 2 because it's a sharp point. You can't say that at x equals 2 the graph is going down, or you can't say that it's going up. It's neither. The derivative does not exist. So, not differentiable. Sharp turns. Anytime you see a graph that has a sharp turn, it's not differentiable. Is the absolute value function continuous? Well, yes it is, because I can draw this curve without ever lifting up my pen or pencil. But it is not smooth because of the sharp point. Therefore, not differentiable. Example number 2. F has a discontinuity at x equals c. Well, this should already pop out to you guys. What do we say a differentiable function is? It's smooth and continuous. If it's not continuous, then it's not differentiable. Plain and simple. So let me go ahead and add on to this. If a function is differentiable, if a function is differentiable, then it is smooth and continuous. Okay? Now, I can also say it the other way around. If the function is smooth and continuous, it's differentiable. So if a function is differentiable, that means that the graph is automatically continuous because of the criteria that differentiability has. But you cannot say it the other way around. You cannot say continuity implies differentiability. You cannot say that. Okay? Take a look at example number 1. That's a perfect example. Example number 1, we have a continuous graph, but it's not differentiable because of the sharp point. Example number 3. F has a vertical tangent at x equals c. Well, we all know that tangent lines represent derivatives, but not every derivative can be defined. For example, this dashed line right here is the tangent line at x equals 1. But what is the slope of a vertical line? You guys should have heard about vertical slopes. It does not exist. How do you find the rise if the rise is continuous forever? There is no rise over run. Okay, so the derivative, I'm going to say derivative is undefined, therefore not differentiable. Example number 4, we have a cusp. A cusp is when two curves meet at a point that creates a sharp point. So notice, I have a curvy part here from the left, a curvy part from the right, and they both met up in a sharp point. So we all know that sharp points means not differentiable. The derivative does exist from the left of one and from the right of one because look, I have a tangent line there, I have another tangent line there, another tangent line there, and another one here. And same goes for the right side. I have many tangent lines, except I can't define what the tangent line is at x equals 1. It's impossible. So we say that it's not differentiable. If that sounds really confusing, then just go back to what I just said. Sharp points are not differentiable. So in the next page, we're going to test without a graph. We're going to test to see if a function is differentiable at a certain point by using the alternate form of the definition of derivative. Now, in the last video, we talked about derivatives. There was two formulas. The first formula was f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, these two represent the derivative, but except that this bottom one represents the derivative function. Oops, function, not fiction, function. Okay? This derivative formula represents a derivative value. Derivative. Okay? Derivative value. In other words, you get a number. How can you distinguish the two? Well, pay attention to the x. We don't know what x is, so we call this a function of x. It's a derivative of f of x. Look at this one in here. That one has a number c inside. Okay? You pick any number for c and you're supposed to get out a value.